It's going to be a little lighter than the last talk. I hope you guys are okay with that. We're going to talk about iterating over statistical models. And why are you listening to me? I developed Stan. I'm a researcher at Columbia, not really a postdoc. I'm a co-founder of the Stan group, which we do some training, some statistical support, and that's all my contact information. But you have no choice. You're all listening to me right now. All right, let's get into March Madness. How many of you have heard of it? Yeah? All right, cool. All right, so what is March Madness? And honestly, this is a very personal question. For me, it's 4 weeks of my life that I can't get back because I'm glued to a TV. I'm usually at a bar by about 11 to start watching these games. It used to be 9 on the West Coast, but I'm here now. It's a time to find love. You root for these teams. You get heartbroken. You really want these, and you see underdogs and heroes come up, right? So if you're not into sports, this is March Madness, right? You just see this big bracket and you don't know what's going on. It's a 64-team tournament plus 4 extra teams. They're the little top teams up there. And the idea is to try to predict who's going to win the national championship, right? It's just a straight single elimination tournament. Just so we can use an example, we're just going to look at the final game here, which is Villanova versus North Carolina. It was an excellent game, but it was the end of this whole tournament. Both of those teams had 5 wins in a row at the end of this tournament, and the question really is, what's the probability that Villanova wins, right? 1? There's a 1, so you know what's going on. Good answer. Right, but anyone that hasn't seen the game, didn't know that it ended on Tuesday night, right? What should you have believed? And really, if you think about it, right, this is what happened at the end of the game. A minute left, it was a 1-point game. 2 free throws later, 35 seconds left in the game, and so Villanova's up 3. A layup happens with 23 seconds left, right? 23 seconds. Villanova goes up 3, right? So now if you're thinking about probabilities, like what's the probability that Villanova is actually going to win this game? With 6 seconds left, it's tied. It was a double clutch 3-point shot. It was crazy. They tied it. It happened. Game over. Buzzer beater 3 to win it. It's one of the greatest championship games in the history of NCAA tournament. It's awesome, right? All right, so if you go back, what was the probability that, you should have called, right? Was it 1, right? Before you saw this game, should you have just said, Villanova's going to win this for sure? All right, so we're going to talk about statistical modeling, and what I really want to talk about is iterating over statistical models. What the point of this talk is that we should start treating statistical models as code. Right? Writing code is a discipline. There are these books, Pragmatic Programmer, Refactoring, Clean Code, a whole bunch of other discipline-like books. But really, it's not really a discipline. It can be a discipline. You have to be really disciplined to make it a discipline. There are design patterns, you got a test, you got a code review, so on and so forth. What do we do about stats? Is stats really a discipline? Right? We've got Andrew's books here, Bayesian data analysis using regression and multi-level models. Right? A lot of the times we think of modeling as sort of a black art, right? It's black magic. You kind of pull out likelihoods and priors out of a box. Models have names, and we don't often share these names across different communities. For example, kriging that geophysicists used is the same as Gaussian processes now in the machine learning community. You got IRTs in the educational community. That's the same as Bradley-Terry models, right? We haven't decided on these names. There's also this added difficulty of statistical models and writing them out and then doing the implementation of them, so trying to get the inference engines out of them. And who here actually collaborates on the statistical models, right? Or is it mostly you go away for a week and then you come out with this magic thing and then that's it. Right, so what do we need to do? We should really elevate statistical models to a first-class entity, right? We need to treat these as things that we should version, like Justin said earlier. We should be able to modularize them from our code, like separate them out, version control them. We should have the language to be able to discuss the differences between different models and actually start discussing the subtle details. Two models that look the same from the surface may not be the same. And one of the benefits of this is that you get to start collaborating. You get to talk to other people that are working on similar models. I work on Stan, and I think Stan gets us pretty close. So if you haven't heard of Stan, it's a statistical modeling language. You get to specify whatever statistical model you're interested in. It's its own language. It has its own grammar. It's not R. It's not bugs. It's just something else. There's integration into R using RStan. There's also other packages like ShinyStan. There's RStudio integration, which is cool. There's RStan ARM, which makes modeling a little easier. It's open source. And one of the benefits is that a Stan program is actually just plain text. You can diff it. It looks like code. By the way, Stan isn't the only thing you should be doing this with. You could do this with linear models, whatever you want. All right, so let's get back to basketball. We're going to start modeling basketball. Before we do that, let's get into a little bit of the history. It started in 1891. It was invented as non-contact conditioning for winter for athletes. And it started with 13 simple rules and a peach basket, right? You shoot the ball into the basket, and that's it. Game over. Well, they get on a ladder, pull it out. One of the funny things is, right, in the original rules, the umpire shall be the judge of men, right? It's not something you'd see in today's game. And in fact, today's game is completely different. You have two 20-minute halves, increasing score, right? There's no takebacks. You can't get minus points here. Points now increment by 2, 3, and 1. It used to just increment by 1. There are 5 players on the court with unlimited substitution, so this isn't like soccer. On the 5th foul, personal foul, you get disqualified from the game. And there's this weird thing called bonus. Within a half, if your team fouls the other team, the 7th time that you foul them, they get free throws. You get 1 and 1. The 10th, they get 2 free throws. Right, these are all complications that are with the basketball game today, right? So if you were to model the 1891 basketball game, that's different from today. All right, so what data do we have, right? There are 351 NCAA Division I men's basketball teams, 33 conferences. Each winner of the conference makes it to the tournament. So that big bracket, 33 of those teams are already slotted by the winners. There are 5,400 games, and each team you get to observe 24 to 35 times. At most, you see a single matchup 3 times, right? So, concrete example, let's say we were to take everyone here and play rock, paper, scissors as a tournament, or as a season. Every group of 10, you're in one conference, right? And you're gonna play each other 2 times each, right? And then you're gonna, at every lunch break or whatever, you're gonna play someone random, right? And that's the data we get to work with. Here's what it looks like. So this are for each row and each column are each team. And the white dots are when they've played each other. You can kind of see how sparse it is, right? If Jared and I were to play rock, paper, scissors, and you saw us 3 times, can you actually tell who's gonna win the 4th? It's actually a really, really hard thing to do. Maybe if you saw me play, someone else a whole bunch of times, you might have a chance, but that's the problem that we're dealing with. So, quick question. Who thinks this is big data? Show of hands. No one. I didn't, but good point. This is actually a trick question. Right, so there's this idea of tall data and wide data. Tall data is lots of replications. How many of you have heard of the Harlem Globetrotters? Yeah, that's most everybody. Okay. They've beaten the Washington Generals 16,000 times. All right. So, that's lots of replications. You see the same team over and over and over again. Wide data is what we deal with. It's lots of fields. You see 5,400 games. You see all these things. That's a day on which they played, whether they're home or away, the score, whether they went into overtime, field goals, so on and so forth. Right? But this isn't the complete set of data either. We could have gone back and looked at video footage and looked at who's on the court at what time, what offense are they playing, what defense are they playing, are they in bonus, are they not? Right? We can continue to model this data or find more data to model, so on and so forth. All right, so this is from Andrew's book, BDA. There are 3 steps in Bayesian data analysis. First, set up the full probability model. 2, condition on observed data. And 3, evaluate the fit of the model. All right, so the first, we're gonna write a Stan program to write the full probability model. Second one, we're gonna condition on observed data, and in this case, we're gonna use RStan to run it. And then we're gonna evaluate the fit of the model. That's using R, ShinyStan, other posterior predictive checks, so on and so forth. Right, but what this doesn't tell us is, once you're done, is that it, right? And the answer is no. This applies to everything that I work on with Andrew. As soon as we write one model and get to the end, that's not it. Tomorrow we're thinking, there's something I missed. There's another bit of dependence I can model. So let's start iterating over models. This is the first statistical model. Here are some of the key assumptions. Only the 2015-2016 season matters, so we're going to throw away all the rest of the data. May or may not be a good idea. Right? Teams have a latent ability, and we're going to call this thing a logistic regression. It can also be called a Bradley-Terry model in this case. So why is our observation so in this case, whether team 1 won or lost. If team 1, it's a 1. If team 2 won, it's a 0. We're going to believe that theta 1 is team 1's latent ability. Theta 2 is team 2's latent ability. And now the difference between their latent abilities is going to give us, we're going to take the inverse logit and give us the probability that, team 1 or 2 won. Everyone okay with that so far? So this is what it looks like in Stan. It's actually pretty easy. One thing that I didn't, sorry, how do you go back with this remote? Red? All right, cool. All right, one thing I didn't mention here was priors, right? So even though I called it logistic regression or a Bradley-Terry model, and that might be common use in certain fields, this model here is a different specification than what me and a collaborator might say. What Stan gives us is a way to actually write it down and actually discuss it. If you remember from Andrew's talk yesterday, that's his new favorite prior here. Right. And yeah, that's it. I get to run it. It takes about 20 seconds to fit. Right. I've done the data munging outside of this thing. The NCAA.stan is that file, and it's now being version controlled, and we're collaborating with other people on this. And yeah, so team 326 happens to be Villanova, team 205 is North Carolina. And you can see under this model, Villanova has a much higher team ability than UNC. Right, so if you do the calculation, probability that Villanova beats UNC is 0.73. Now, is that a good prediction or not? It's hard to say, right? Like, we know what happened at the end of the game. It was down to a coin flip. I don't know if I actually believe that, but that's what our model says. This is a view of what ShinyStan will give you. It's showing us, just these 2 parameters, but it can display more. This is showing us the joint distribution of the 2 parameters. I'm Bayesian, so I'm interested in posterior distributions of these things. You don't have to be. That's fine. You can use Stan for non-Bayesian things. All right. So, how did we treat this as code? The statistical model went into a separate file. We used Stan. It just went off. We use Git, makes us able to diff code, collaborate. Testing, we ran it, and then we inspected the fit. We back tested on historical data, it looked okay. Priors, we change priors all the time. Model number 1. So I called this model number 1. Honestly, this was about the 10th model that we fit, right? Just add a 0 to all the numbers that I put up. Right, and here's a key thing in writing and editing. In writing, you must kill all your darlings, right? So get used to writing out a statistical model and just tossing it away, right? It doesn't explain enough. Don't be afraid to just like whack it and get rid of it. So number 2, there's this well-known effect of home court advantage, right? At least in the NCAA game. It's about 4 points, right? 4 points is really huge when you think that a lot of games come down to buzzer beater 3, right? So we're gonna do this. I've now added an alpha, right? That's the home court advantage. It's still called a logistic regression, and you could still call it a Bradley-Terry model, but this is completely different. If you look, the only difference is I've now added a new data variable for whether or not they were home, away, or in a neutral court. Added a new set of parameters, and then added Andrew's favorite prior, right? So I quickly went from a normal logistic regression to, is this in some other package? I honestly couldn't tell you. All right, this also took about 20 seconds to run. And here now you see that Villanova beats UNC, and the prediction's about 52%, right? But, we're iterating over all these models, right? We're gonna check the fits, and turns out that this model is actually kind of wrong. If you look at the home court advantage, you expect it to be around 0, right? We know that the home court advantage is really about 4 points, but it's all pushed up about 6 and 7. That's really weird. We couldn't figure this one out, so we ditched it. All right, model number 3. Once again, this is really close to model 30. If you look at our commit log, we're just continually updating our models. Still the assumption that 2015, 2016 matters. Teams have a latent ability, and we're gonna model the point difference between team A and team B, team 1 and team 2. And we're also gonna have this home court advantage. Right, in Stan, it's really simple. Instead of looking at the wins as Bernoulli logit, we're just gonna treat it as normal. So now that's it. The generated quantities block here is to calculate the probability of wins, the posterior probability wins, just because it's hard to calculate otherwise. And now you see something like that with Villanova winning, just, losing. But not by much. This is what it looks like in Shiny Stan. And how did we do? To be honest, we didn't do that great. We entered the Kaggle competition. There was one that evaluated on log loss. I can tell you why. First, we were actually not solving the problem that Kaggle asked us to solve. They asked us to solve log loss over this whole tournament. We were trying to evaluate how good basketball teams are between each other using this sparse data. Right, so the first thing to do is, actually try to answer the question. But, that one's tough. I like basketball, right? I'm more interested in seeing who's a better team than trying to predict these things. So, all right, maybe next year we'll do better. We actually improved this model a lot more, and it's a lot harder to explain, but we modeled the points for against the points against and modeled those independently. We've got a structured thing. They all do about the same. It's hard because there's so much uncertainty about who wins these games. The key takeaway is treat statistical models as code, right? So actually start treating it as a first-class entity. Don't just hide it inside an R script and, that's not good. Thank you very much. This was definitely a collaborative effort. Rob Trangucci really helped me build all these models. He actually built all the models. I just talked about it. That's a Stan team. Rob's on there, I'm on there. If you need help with Stan, go find our webpage. Our users mailing list is great. There's stand group information and my email address. Thank you.